when 0.860 grams of a pure liquid consisting of carbon, hydrogen, and oxygen was burned completely. 1.64 grams of CO2, 1.01 grams of water were produced. What is the empirical formula for this compound? Our starting chemical, we're told, contains all three of these elements, carbon, hydrogen, and oxygen. So we can write our generic chemical formula as C sub X, H sub Y, O sub Z. And the goal again here is to determine, let's put arrows here for all three of my subscripts, moles of each element in 1 mole of the compound. So we need to determine moles of carbon, hydrogen, and oxygen. So how are we going to do that? Well, we're told that the chemical reaction is a combustion reaction forming carbon dioxide and water. Let's rewrite things here so we have a very clear picture of what's going on. C sub X, H sub Y, O sub Z. Combustion reactions always require oxygen, so that's our second reactant. Products are always going to be CO2 and H2O. And in the problem, we are told that we started with 0.860 grams of pure liquid. So let's write 0.860 grams above the compound. We're also told that we collected the products and we got 1.64 grams of CO2. So let's write 1.64 grams of CO2. And we also collected 1.01 grams of water. 0.01 grams. So our CO2, all the carbon in this compound, forms CO2. So if we can determine the number of moles of carbon in CO2, we'll know how many moles of carbon we had in our starting material. The same is true for water. For hydrogen. All the hydrogen in water came from the hydrogen in the compound. So if I can determine how many moles of hydrogen I have here in my 1.01 grams of water, that'll tell me how many moles of hydrogen I have in the compound. Oxygen, not the case. I've got oxygen from two sources, from the compound and from the atmosphere, required for the combustion reaction. So I got to get oxygen by difference. So let's start with the easy stuff. Let's start by calculating moles of carbon. And moles of carbon, our starting point is 1.64 grams of CO2. CO2, of course, is not carbon. So we have 1.64 grams CO2. We now want to convert that to moles of CO2. 1 mole of CO2, and I'll leave it to you to verify, has a mass of 44.01 grams. Grams cancel. But I want moles of carbon. So I see that I have 1 mole of carbon in every 1 mole of CO2. So I'm going to write 1 mole carbon over 1 mole of CO2. Moles of CO2 cancel. I now have moles of carbon. So when I do the calculation, I get 0.0373 moles of carbon. Now let's do the same thing for hydrogen. Moles of hydrogen. Our starting point is going to be the mass of water, since that's where hydrogen is located, and we have 1.01 grams of that. Grams of H2O. Again, this is over 1. Molar mass of water is 18.02 grams, so 1 mole of H2O contains 18.02 grams. You want to convert grams of H2O to moles of H2O, but I want moles of hydrogen. I see that there are 2 moles of hydrogen in every 1 mole of water, so I'm going to multiply this by 2 moles of hydrogen for every 1 mole of water. Moles of water cancel. Now I've got moles of hydrogen, and when I do the calculation, I'm going to end up with 0.112 moles of hydrogen. So we now have moles of carbon, moles of hydrogen. We can't get moles of oxygen by the same approach because, as I already mentioned, we have oxygen coming from 2 places, from the compound and from the oxygen in the atmosphere supporting the combustion reaction. We have to get the mass of oxygen first by difference. if we calculate how many grams of carbon and how many grams of hydrogen are in this compound, subtracting that from my initial amount of the unknown material will give me the mass of oxygen. So let's do that. So I now have to convert my moles of carbon and moles of hydrogen to grams of each. So grams of carbon is going to be equal to 0.0373 moles of carbon, that is to say the number of moles we just calculated, times the molar mass, 12.01 grams of carbon in 1 mole of carbon. Moles of carbon cancel. When I do the math, I get 0.448 grams of carbon in this compound. For hydrogen, the same type of approach. My grams of hydrogen is going to equal the number of moles of hydrogen that I calculated in this compound, which is 0.112 moles of hydrogen, times the molar mass of hydrogen, which is 1.008 grams of hydrogen per 1 mole of hydrogen. And doing the math on this, we get 0.113 grams of hydrogen. So we also know that there are grams of oxygen, and when we add up all 3 of these, we're going to end up with our 0.860 grams of the compound that we started with. So these 3 have to add up to 0.860 grams of the compound. Well, we're going to subtract then these 2 grams of carbon and hydrogen from the mass of the compound to get our grams of oxygen. So let's do that. So we're going to take our 0.860 grams. We're going to subtract from that 0.448 grams of carbon, and then we're going to subtract again from that 0.113 grams of hydrogen. So now when we do the subtraction here, we're going to end up with 0.299 grams of oxygen. So now that we have grams of oxygen, we can convert to moles of oxygen, because that's what we want, using the molar mass. Why do we want moles of oxygen? Let's go back and review. Our subscripts here are moles of each element in the compound. We already calculated the moles of carbon. That number is, let's highlight it. Moles of carbon is given right here. We did that calculation. Moles of hydrogen, we have that right here. Moles of oxygen, we've got to calculate now because we just now calculated how many grams we have in the compound. So let's do that conversion. 0.299 grams of oxygen, that's over 1, times 1 mole of oxygen has a mass of 16.00 grams. Grams of oxygen cancel, and now when we do the division on that, we get 0.0187 moles of oxygen in this compound. Let's highlight that. So now we have the moles of all 3 elements that we're interested in this compound. So let's list them here now, because now we have to find the smallest whole number ratio. So we have carbon, we have hydrogen, and we have oxygen. Let's just put a dash there. Oxygen, let's do that here because I got the number right here. 0.0187 moles. Let's scroll up now and get those moles of carbon and hydrogen. We have them highlighted in yellow. For carbon, we've got 0.0373. 0.0373 moles. And for hydrogen, let's go back up and get that number, 0.112. 0.112 moles of hydrogen. So how do we do this? We again look at the number of moles and find the smallest number of moles that we have, and that falls to oxygen. We have the smallest number of moles of oxygen, so we're going to divide all 3 of these then by that number, 0.0187. Divide this by 0.0187. Divide this by 0.0187. And now when we divide these, our first division is going to give us 1.99 moles. Our hydrogen division is going to give us 5.99 moles. And of course, our oxygen has to give us exactly 1 because we're dividing by the same number. We can round our 1.99 to 2. We can round our 5.99 to 6. And of course, 1 is going to stay 1. So I now have my smallest whole number ratio. This worked out nice. 2 moles of carbon, 6 moles of hydrogen, 1 mole of oxygen. So this is my value for subscript X. This is my value for subscript Y. This is my value for subscript Z. And now just putting these numbers into our chemical formula, we have C2H6O. So this is our empirical formula for this compound.